Hello and welcome to the lecture of linear algebra. In this lecture, we will talk about diagonalization. Diagonalization of the matrix. Diagonalization of a matrix is carried out for numerous purposes. One of the purposes, if you want to calculate a power of the matrix, diagonalization helps you in simplifying those calculations. It is also very useful in context of transformations, linear transformations, because it simplifies to a certain extent the task of carrying out the transformation from one subspace to another subspace. So, as in the last lecture we talked about the similarity measure, in which we said that if a matrix A is similar to uh, B or B similar to A. In this case, if we use that situation, we can say that a matrix A can be diagonalized into a matrix D if A is similar to D. Right? So if A is similar to D, a square matrix A is said to be diagonalizable if A is similar to a diagonal matrix, um, that is A is equals to PD, P inverse, and of course here P has to be invertible matrix. uh, so for example, uh, we know that let's look at the first instance where this diagonalization can be helpful. Let's assume that we have a diagonal matrix which is 5 0 0 3. So if I take the square of it, right, so it will be 5 0 0 3 multiplied by 5003. So you can easily see that this is 5 square 0 uh, 03 square, and similarly d cube will be 5 cube 0 and 3 cube. Now if let's say this diagonal matrix is similar to A, it means that A is equals to P dP inverse. We can say that finding the power of A is also very similar once once we know the p's. So let's do the example, another example, to illustrate if how diagonalization help in calculating the power of that signal. So if A is, let's say, 7 minus 4 2 and 1, so you have to find the formula for A of k. K is the power of this matrix, and such that A is similar to D, which is PD P inverse. So in the first instance, if we are able to diagonalize A in terms of D, we know that D finding the power of D is very simple, right? So uh, luckily in this scenario P is given to us, and in the next in shortly we will see that these are nothing but uh, eigenvectors of A. Okay, now and D is that. So it means P inverse is also quite simple, which is changing here my position here, and you've got here minus 1 and 1. Okay, now similarly, um, we have A square as nothing but PDP inverse into PDP inverse. So if I multiply them up, so this is P inverse into P will be an identity matrix, and that will be quite easily PD into identity matrix, and you can say D into P inverse, right? So now this is nothing but equal to D square, so it comes out to be P D D P inverse, right, which is nothing but equals to P D square P inverse, right? And we can easily find that 1 minus 1 1 minus 2 5 square 0 0 3 square and 2 1 minus 1 minus 1. And similarly we can find a cube as you can write this as PD P inverse into a square, and if I do that, that becomes PD P inverse, and again this is PDD P inverse. Now again this is an identity matrix. We have now here is P D D square into P inverse, rather than I think should write as D square, and again this is PD square P inverse, which is nothing but PD cube P inverse. So similarly we can generalize A of k as nothing but equals to P times D of k into P inverse, right? So that's what we're going to have. Uh, that's how you can simplify the calculation, because we know that the diagonal, it is very easy to calculate the power of the diagonal. So once we have um, developed a diagonal matrix or diagonalization of A, right? So one we have to do is simply multiply P and P inverse with that diagonal matrix. Of course, the power that you want to calculate is also d to the power k. Now, the diagonalization theorem states uh, that if A matrix is diagonalizable, A is diagonalizable um, only. We know that if A is diagonalizable only if A has an linearly independent eigenvectors. So A is only diagonalizable if it has n linearly independent eigenvectors. In fact, I mean, if you want to be exact, we can say that A is equals to P D P inverse, with D being the diagonal matrix. Actually, we are saying that if P uh, if the columns of P, actually should be, if the columns of P are n linearly independent eigenvectors of A. So in the previous example, if you look at this example here, what we are saying that from this context, that this matrix can be diagonalized to this form only and only if the eigen vectors are linearly independent and the columns of P are actually the eigenvectors of this matrix A. Okay, so we can say that this is let's say that it will have two eigenvalues, lambda 1 and lambda 2, right? And this is the vector corresponding v1 for lambda 1 and v2 for lambda. So this will be a v1 and this will be v2, right? So eigenvectors of A. Uh, so in this case, luckily in this case, uh, the diagonal entries are nothing but the eigenvalues of A in D are nothing but eigenvalues of 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 A. And of course, the corresponding vectors for those eigenvalues will be in P, right? Uh, so to sum up, we say that A is diagonalizable if and only if there are actually enough eigenvectors to form the basis of R of n, right? Because A is n by n. This is a very important point. You have to remember that n cross n matrix, right? So only situations in which this diagonalization can happen, uh, that because the matrix P will have n independent eigenvectors, means it will should form the basis of R of n actually. So these are the values of eigenvectors. These are contains eigenvectors, so it means those vectors uh, should span Rn, and similarly dr are the eigen values of A. So coming back to the example here, so uh, so what we are saying that if this A is a matrix, if A is that matrix here, right, and the P matrix, if A is similar to D, then P matrix will contain the eigenvectors of this matrix A, V1 and V2, and they must span R of n. So you can see here these are two independent vectors. These are two independent vectors, this and this. It means its dimension is 2. It means they can actually span R of 2. Similarly, these d values, the values in d 5 and 3 are the eigen values of A. We can easily very easily can find it out. I'll just find it out in few moments. Uh, so it means that for A to be diagonalizable, A is only diagonalizable if and only if there are enough eigenvectors to form the basis of R of n. So if it means that this vector should be linearly independent, then they can only form the basis of R square. If they are not linearly independent, this cannot form the basis of R of n, and of course it means that P is not invertible. Okay, then P will not remain invertible if these two vectors are linearly dependent, right? So it means there is no similarity between A and D. Uh, Similarly, the resulting eigenvectors, we call them uh, bases. Uh, Actually, eigenbases of R to the power n. Eigenbases of R to the power n. Okay, we can easily prove that. Um, uh, Say, for example, if uh, A is a matrix that is given to you, and we say P is another matrix which has eigenvectors of A as its columns, then we can say that A times P will be A V1 V2 up to, of course, it's n cross n, so this should be equals to n, right? And this means the resultant thing here is AV1 AV2 up to AVn, right? And similarly we can find out PD. Now we said that P is again V1 uh, up to Vn, and diagonal matrix is nothing but the eigenvalues, which is lambda 1 up to lambda n, and all the remaining values are zeros, right? So if I multiply those two vectors here, what I'll get here is lambda 1 times V1, lambda 2 times V2, and lambda n times V. Right? Now see, because uh, uh, lambda is the eigenvalue, it means we know that AV1 is nothing but equals to lambda V1, AV2 is equals to lambda V2, and AVn is equals to lambda nVn. It means AP is equals to nothing but PD, right? And of course, if you multiply the inverse from the left hand side, the answer here is PDP inverse. Okay, and of course P inverse has to exist. It means if P inverse has to exist, it means the n independent there should be an n independent eigen vectors of A. So we can now do multiple examples to illustrate what we have just said, and we can now carry out the diagonalization of any matrix A. Okay. So if A is equals to 1 minus 3 3, 3 minus 5 3, and 3 minus 3 1. So first thing we have to do is to find the eigenvalues of A, and that we can do using characteristic equation, which is nothing but delta determinant of A minus lambda I. In this case what we will have here is um, lambda as so we can take determinant of A minus lambda I, which is determinant of 1 minus lambda 3 3 minus 3 minus 5 minus lambda minus 3 3 3 and 1 minus lambda, right? Now if you take determinant of it and you solve it up as in your book, the answer you will get here is minus should be equal to 0, so minus lambda minus 1 and lambda plus 2 whole square equals 0. So now it has got uh, two eigenvalues, which is lambda 1 is equals to 1 and lambda is equals to minus 2. Now the multiplicity of this minus 2 is 2, so we can say that lambda 1 and lambda 2. So this has a multiplicity, algebraic multiplicity of 2, right? Now what we have to now do is to find the corresponding eigenvectors for lambda 1. So to going to find that corresponding eigenvectors, what we simply have to do is a minus lambda 1 times I into v 1 should be equals to 0, right? Now in that case this is nothing but equals to, if you put 0 1 here, answer you get here is 0 3 3 minus 3 minus actually 6 minus 3 3 3, and you will have a 0 here, okay, and that would be v1 equals 0. Now this is equal to finding the solution to the homogeneous equation for three points in v1. Now if you solve that, the answer, the non-trivial solution that you will get here is um, simply uh, v1 is equals to 1 minus 1 and 1. Okay, you can go at your home, you can do it as a practice and solve it yourself, but here since I'm demonstrating only the concept, so you can take that as an assumption that what I'm writing here is correct. Okay, now basis, similarly we can find the basis for lambda is equals to minus 2, and of course you have to do the same thing here. Luckily in this case we got two eigenvectors correspond, because it has algebraic multiplicity of 2. It has now it has got luckily we have got two eigenvectors corresponding to that, that is minus 1 1 0 and another v3 is equals to minus 1 0 and 1. And if I write v1 again here, so v1 is equals to 1 minus 1 and 1. Now we can see that v2 v1 v2 and v3 are actually linearly independent, right? Now so it means we can substitute that, and we can write this as it can be used to construct the p matrix, which is minus 1 1 0 sorry minus 1 minus 1 1 minus 1 1 0 minus 1 0 and 1. And of course d value can be nothing but the eigenvalues here, which is 1 0 0 0 0 minus 2 0 0, and because it is the algebraic multiplicity of this eigenvalue has an algebraic multiplicity of 2, so you got must be here 2 times. So this is uh, which is nothing but equals to uh, p and d, right? Now either you can show that it a is equals to p d p inverse, or the easier way around is a p times p d. So at home and in the book that you can do it to yourself and find out that a p in this scenario is nothing but equals to p d, right? Now similarly we can do another example and try to diagonalize another matrix. um, let's say A, which is nothing but equals to 2 4 3 minus 4, minus 6, minus 3, 3, 3, and 1. Now again, so first thing you have to do is to find the eigenvalues of this matrix, which is it, again determinant of a minus lambda I should be equal to 0, and which in turn is nothing but equals to uh, determinant of 2 minus lambda 4 3 minus 4 minus 6 minus lambda minus 3 3 3 and 1 minus lambda, right? Now if you solve them up and try to find out the corresponding value of lambda, what you will get here is again this kind of characteristic equation. I'm writing it here, you can solve it yourself as a practice. And so the answer here, the lambda value that we get here is lambda 1 is equals to 1 and lambda 2 is equals to minus 2 with algebraic multiplicity uh, of 2. Okay. Now in the first case, so what we have to do now is to find the eigenvectors. So let's try to find the basis for lambda is equals to 1. So if I put here determinant is equals to not determinant here, actually you will have now as 1 4 3 minus 4 again minus 7 minus 3 3 3 and 0 here. Okay, and this have to v1 should be equals to 0. Now let's solve this one and let's try to find it what is the corresponding v1 here. So this is actually what you can do here is simply um, multiply with 4 or make an augmented matrix first, multiply first row with 4 and add it to the second row, and similarly multiply first row with 3 and add it in the third row. Okay, now so I'll do that in the same step here, which is which comes out to be again will be 1 4 3, and then you have an augmented matrix 0 0 0, and if I method 4 added here, I'll have 0 here, and then I'll have 16 and minus 7 plus 16 will be 9, and then 12 minus 3 would be 9 here, and then again multiplied by 3 and subtracted this time, so that would be 0 here. So this is be 3 minus 12 is minus 9, and of course 3 will be again 0 multiplied by 3 is again minus 9 here, right? So if I so it means second and third row are the same, I can add them up here, and that leads me to 1 4 3 0 0 0 and 0 9 9 0 0 and 0, right? So now actually we can see here that we can have x3 as a free variable. So if x3 is a free variable, then I can simply write that here as x1 is equals to minus 4x2 minus 3 x3, and x2 is equals to minus x3, right? So if I write this as x1 x2 and x3, the solution here I'll get here is as nothing but equals to minus 4 oh sorry, this is x2 is equals to minus x3, so you can turn it down here, which becomes again simplifying that, so u plus x3, and this is nothing but equals to x3. Okay, so here I can write this as x1 is x3 minus x3, and then of course this is an x3, which is nothing but equals to 1 minus 1 1 and x3, right? Now this is the eigenvector v1 corresponding to lambda 1. Similarly, I can solve for lambda is equals to -2, right? And the matrix that I had, if you remember, so what I'll get here is for lambda 2 is equals to -2, that I will have 2 minus lambda as 0, 4, 3, minus 4, minus 6, and when I add minus 2 this is plus 2, it becomes minus 4, again minus 3, 3, 3, and 1 minus, and effectively plus 2 is actually 3. Okay, now again this v2, uh, sorry, x should be equal 0. Now uh, the corresponding value, of course, um, here would be, what you have to do is simply so take that, I can replace the first row with second row and all that, but so 3, 3, 3, and then you can have as again as 0, 4, 3, and you get minus 4, minus 4, minus 3 into x2 equals to 0. Okay, now I think there is a small mistake here. This 2 minus lambda, and lambda is actually minus 2, so that would be, sorry, my bad, that would be plus 4. So this step is wrong, sorry about that. So and again minus 6 minus, okay, plus 2, that's alright, and 1, okay, that's alright. So it means now I can actually add the first row with the third row with the second row, so that leads me to 4, 4, 3, 0, 0, 0, and 3, 3, 3, um, and of course I have the augmented vectors as this here. Similarly, I can multiply this by 4, this by 3, and subtract them here, which leads me to 4, 4, 3, 0, 0, 0, and this will be 12 minus 12, that will be 0. This will be 12 minus 12, that will be 0, and this will be multiplied by 4, multiplied by 4, which is 12, multiplied by 3, which is 9. So 12 minus 9 is actually 3. So here I have um, 3 actually. We can see here that my the point x3 uh, is 0, right? So that means just let me write it again over here, which is 4, 4, 3, 0, 0, 0, and you have 0, 0, 0, and 0, 0, 3. Now that leads to the last term 3x3 equal to 0. It means x3 equals to 0. That means I'm left with only 4x1 plus 4x2 is equals to 0. It means x1 is equals to minus x2. So the only thing, so if I wanted to generate two vectors, right, I must have two free variables, but in this case I only have one free variable, which is x2. So in this case x1, x2, and x3 is nothing but equals to minus x2, and then you have x2, and then you have 0. So resulting vector is minus 1, 1, and 0, which is x2 here. So this is your vector corresponding to v2. So in this case we only have one eigenvector, and the multiplicity of that eigenvalue for which this eigenvector corresponds to is 2. So it means for those two eigenvalues I can only have two eigenvectors. Now if you remember that we in the theorem that we just discussed, that for A to be diagnosable, uh, this eigenvectors corresponding to values of A should form the basis of R of n. So in this case on we have we actually the vector exists in 3 dimension, so it means it's R3, and we have only two vectors. So two vectors cannot actually form the basis of R3. So it means they can form the subspace. They can span the subspace of R3, but not R3. So the actual point here is that these eigenvector has to span R3, not its subspace. So this means this vector is not, this vector A is not diagonalizable. So we can say that, and we can also further simplify and exactly point out um, the conditions for diagonalization uh, of actually A. Okay, which are, so we can say that if A is an n cross n matrix, if A is an n cross n matrix, uh, uh, whose whose uh, whose eigenvalues are uh, lambda 1 up to lambda p. Of course, if all of them are distinct, then p ideally should be equals to n. But if they are not equal, then um, it means there are some value which will have some kind of uh, algebraic multiplicity, and that would lead to a much different scenario uh, that we will just explain in a few moments. Sorry about that. No. So if A is an n by n matrix um, whose values are lambda 1 to lambda p, of course, if all of them are distinct and all of them are different, then p should be equals to n here. But there are some values which have some kind of eigenvalue which have display some kind of multiplicity. Um, so we say that um, first thing, that for 1 less than k less than p, uh, the dimension of the eigenspace for lambda k is less than or equal to the multiplicity of the eigenvalue So for any kth value between 1 and p, we say that dimension of the eigenspace of lambda k is less than or equal to the multiplicity of the eigenvalue of lambda k. So it means in the last examples we just did, we see that we just saw that though lambda is equals to lambda 2 is equal to minus 2 has an algebraic multiplicity of 2, right? But the vectors that we actually found out was equal only 1, right? But in the previous example before that, we found out that though uh, the so the here also lambda minus 2 has the algebraic multiplicity of minus 2, but the number of eigenvectors that I found out is actually 2. So this actually statement, the statement here actually puts a condition here: the dimension of the eigenspace for lambda k is less than or equal to the multiplicity or eigenvalue of lambda k. So it means the number of maximum vectors that you can have corresponding to the multiplicity of here minus 2 is actually 2, right? Maximum, right? Minimum can be the minimum is that there is no vector, uh, but there could be only one vector, or there could be only maximum of two vectors corresponding to that eigenvalue, which has some kind of algebraic multiplicity, right? And we know that dimension, so these vectors will form a subspace, and we know the dimension of a subspace is the number of linear independent vectors in that subspace. So in this case, corresponding to lambda 2 is equal to the eigen subspace has a dimension of 2. So that's what he's talking about. The dimension of the subspace of lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. Now, so if we take the second part here, the matrix A is diagonalizable. Second part is the matrix A is diagonalizable if and only if the sum of the dimension of the eigenspaces equal to n. So so in this case, like for example, in the first example that we did, in which we had in which we were able to diagonalize A, remember that lambda 1 is equals to 1 and lambda 2 is equals to minus 2 with a multiplicity of 2, right? So here what we have one eigenvector, and there we had two eigenvectors corresponding to that value. So it means we are saying that the sum of dimensions, so this eigenvalue has a dimension of 1, these eigenvalues have a dimension of 2, because they were existing in dimension, so it is 1 plus 2 will be 3. So it means since it was a 3 by 3 matrix, A was a 3 by 3 matrix, so the dimension of eigenspace actually were equaling to n, which is 3. Okay. Now the C part is okay. There are other parts as well. If this happens, uh, uh, and this happens, this can only happen if number one part is the characteristic polynomial factor uh, factors into and the number two is, that means the characteristic polynomial actually factors into all linear factors, so it means all have distinct values. Or other thing is the dimension of the eigenspace for each lambda k is equal to its multiplicity. So we are saying that because in this example uh, lambda 2 was minus 2 and its multiplicity was 2, it has got now two eigen vectors, or dimension of this subspace corresponding to this lambda 2 is equal to minus 2 is actually 2. So these two things are important for a vector to be diagonalizable, right? Another important point regarding this theorem is that if A is diagonalizable and there is some basis bk is a basis of the eigenspace corresponding to lambda k, right? For each k, then the collection of sectors, then the collection of vectors b1 up to bp forms an eigenvector space for Rn. Like for example, in this example, uh, so basis for this subspace for lambda 1 was this vector, right? It was actually line. Now this was for this vector, for this eigenvalue with the multiplicity of 2, I got 2 eigenvectors. So these are the basis for which is eigen subspace for lambda 2, right? So accumulation of all these three vectors actually form the basis of R of n, right? So in this case it was v1, v2 and v3, and this for one for was lambda is equals to 1 and lambda 2 is equals to minus 2. There was another example in which there was only one vector for lambda 2 is equals to minus 2. Of course, in that scenario A was not diagnosable, right? Let's do an example to illustrate what we have just said regarding uh, these 3 points. So if A is equals to this matrix, which is 5 0 0 0 0 5 0 0 1 4 minus 3 0 minus 1 minus 2 0 minus 3, right? Now we can see that A is a triangular matrix, and since A is a triangular matrix, we can see that the eigenvalues here are the entries on the actually on the diagonal, and both from the point here we see that uh, that 5 there will be a lambda 1 is equals to 5 and lambda 2 is equals to minus 3, and multiplicity of 5 and multiplicity of 3, because we know that for a diagonal matrix, for a triangular matrix, uh, the entries on the diagonal are actually correspond to the eigen values of that matrix. So in this case you can see that the diagonal entries have 5 2 times and minus 3 as 2 times. It means the algebraic multiplicity of this lambda 1 uh, is 2. Lambda 1 is 5 is multiplicity of 2, and lambda 2 is equals to minus 3 has multiplicity of 2. Now we can actually find out the corresponding basis vectors for that, for lambda is equals to 5. So when I do that, right, so it means what should I get here is unfortunately just a second, this handy got. Okay, now so that scenario, uh, the corresponding vectors for that is lambda 1 is equals to 5 would be a minus lambda 1 I into b1, of course, um, that would be equals to um, if I write this up here using this matrix A, which I have just written over here, can write it as this has nothing but 0 0 0 0 0 0 0 and 0. and that would be 1 4, that would be minus 8 0, and minus 1 minus 2 0, and minus 8, right? Okay, now and that should be equal to 0, right? So we can do the augmentation here, uh, and we can easily see that here, right? That I will definitely have two free variables from here, and if you do a slight bit of manipulation here, because I can easily say that because I am seeing actually two free variables in this scenario, so it means I will have at least uh, two basis vectors here, right? So we can simplify it further if you want, and the thing that we get here is added here 0 0 0 0 0 0 0 0, and I can add this third row to the fourth row, and this is 1 4 minus 8 and 0. The answer here is 0. I get here is 2. I get here is minus 8 and minus 8, and of course this is 0 again. Now so I can do a bit of calculation here, in which I can say that of course it's an augmented matrix, if you want to be exact here. So the vectors, I can easily find it out, is um, the first thing from here is that in fact I can take it, replace this first and the second row to make it the pivots, and then it will get here is 1 4 minus 8 0 0 2 minus 8 minus 8, and 0 0 0 0 0 0 0 0, right? So I have nothing but equals to two free variables. So what I can easily find it out, the corresponding values. I think you can do it at home. The values, the vectors that we find out is minus 8 4 1 and 0, which is quite obvious from here, the second equation and the first equation, and v2 is equals to minus 16 4 0 and 1. Okay, now uh, again, um, similarly for lambda is equals to 3, lambda is equals to minus 3, I can do the same calculation here again. And this is a matrix, so a minus 3 lambda uh, 3 a minus 3I into x would be 0, so a minus actually can 3I into b2 is equal to 0. So in that scenario what I'll get here is the matrix which is 2 0 0 0 0 2 0, sorry, minus 3I, so that would be uh, minus 3, that would be then a plus 3I, sorry, that would be 8, that would be 8, that would be 0, and that would be 1 4 0 0 minus 1 minus 2 0 and 0, right? And again here, right, and this should be equal to 0. We can see here again quite easily that it will also have two free variables, um, by the looks of it, and since it will have two free variables, that will make it very easy. I mean, you can do that. I mean, you can say third row, I can add third row with the fourth row, so that will make it much more easier. So if I do that, right, first with third and subsequently, okay, let's do that first, then 8 0 0 0 0 8 0 0, and if subsequently if I add them sorry, add a third row with the fourth row, I will get here is 1 4 0 0 again. I get here is a 0, and 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 2 here, and 0 and 0, and of course it's an augmenting matrix. Then I can further simplify that, and you can make the corresponding pivots, and find out the fit, because you can easily see that there are two pivots, sorry, two free variables, so You can do it at home and you will find out that the resulting vectors should have a form like this. Okay, now we can see that these are two independent set of vectors, and the matrix P you can build from these four matrices which we have just found out, which is equals to so here it is minus 8 4 1 0 minus 16 4 0 1 0 0 1 0 0 0 0 1. Okay, and similarly D matrix is already quite easy to calculate. It is 5 5 minus 3 minus 3, and of course rest of the values are zeros. Okay. Uh, okay. So let's do a simple question. Say if let's say if A is a 4 by 4 matrix, right? Um, whose eigenvalues are, let's say, 5, 3, and minus 2, right? And suppose you know that the eigenvalues of lambda is equal to 3 is two dimension, right? So for the eigenspace for this eigenvalue lambda is equal to 3 is two dimensional. So so do you have enough information? So do you have enough information that A is diagonalizable, right? So what do you think? I mean, I'll give you 30 seconds to judge that if it is diagonalizable or not. It isn't enough information, and A is diagonalizable because the thing here is, if lambda is equal to 3 is two dimensional, it means the maximum dimension, if you remember the B part, or it was A part. Yeah, the A part, right? The maximum number of dimensions could reach up to the multiplicity of the eigenvalue. So it means if it is two dimensional, it is going to be the maximum multiplicity. I mean, if you read it in an opposite way, the 3 will have a maximum, or it will have a multiplicity of 2. So it means there will be one eigenvector for with 5, one 2 with 3, and one with, of course, minus 2. So it means there will be four linearly independent set of vectors, and when there are four linearly independent set of vectors, it means eigenvectors. It means A is going to be diagonalizable and also satisfy the condition stated in the theorem for stated as B and also C. Okay, so this marks the end of diagonalization. In the next lecture, we'll talk about eigenvectors and linear transformations.